Welcome to this lecture series in real analysis. In this lecture, we'll discuss the notion of convergent sequences, which is a central notion in all of this lecture series. So let's recall what we need. We will need what is meant by a sequence. We have done this many times. In short, a sequence in a set X is just a function from naturals to X. Sometimes we may include the zero in the domain, so it may be thought of as a function from whole numbers to X. Or one can think of it as a list of this sort, where this way of expressing things and that way of expressing things are the same. We saw what is the connection. It's a very simple connection. So that's a sequence. We will be concerned with real sequences. So a real sequence is just a sequence with values in R. So if you think of it as a function, it's a function from the naturals to the reals. Or you can think of it as a list, where each element of the list is a real number. So that's a sequence. And we will need to know what is meant by this phrase ultimately and the phrase frequently. So what is meant by ultimately? So suppose we have a sequence in a set X. And once again, this is a notation. This is referring to this list. This means this infinite list. Each element here is an element of capital X. So once we are given a sequence in X and we have a subset of X, we say Xn lies in A ultimately over N if for all natural numbers there exists a natural number at least that much such that, what am I writing? What I mean is this: there exists a natural number such that for all natural numbers at least that much, we have Xn lies in A. So that is the meaning of Xn lying in A ultimately. Beyond a certain point, all the elements of the sequence lie in the set A. Again, we discussed this in detail. And similarly, we have the meaning of frequently. So let me copy the relevant part. So again, the same setting. We have a sequence in a set X and A is a subset of X. We say Xn lies in A frequently if for all natural numbers there exists a natural number at least that much such that Xn lies in A. So there doesn't come a time after which the elements of the sequence stop lying in A. They will always in future come back to A. Okay, so one thing should be clear: if this happens, then this clearly happens. So ultimately, if something happens ultimately, then that also happens frequently, but the converse is not necessarily true. Okay, so once we have all this in our pocket, we can continue. Here are some problems for practice. This one has been marked as star, not because it is hard, but because we are going to use it. It is a very simple, straightforward exercise. Okay. So now we come to the notion of convergence. Fix a sequence in R, and we say that the sequence converges to a point X in R if we are going to write down what happens, but let's see intuitively what we want to do. So we have a point X here, we have some sequence in real numbers, and we would like to say that the sequence converges to the point X if no matter how small of a room we build around the point X, ultimately all the points of the sequence start living inside this room. So if you build let's take epsilon as maybe 1 upon 100. So that's a small neighborhood around X. Ultimately, all the points of the sequence come here. You build an even smaller room, you still find that ultimately all the points of the sequence come here. So one could now say that, or this looks I mean, the phrase convergence is now validated once you have that condition satisfied. The points of the sequence kind of tend to x. They want to become x. Okay? So that's the intuitive idea, but let's write it formally. And it's a very simple one-line thing that we can write down to express the same thing. All we are trying to say is that for all epsilon greater than 0, this happens ultimately over n. You choose an epsilon, you will get this room, and saying this happens is same as saying that xn is inside this interval, right? The distance between x and xn is at most epsilon or less than epsilon, means xn is lying inside this open interval. So once again, we say xn converges to x if for all epsilon greater than 0, this happens, meaning the distance between x and xn is less than epsilon ultimately over n. Maybe this, this ultimately is, of course, one may take a long time to satisfy this for all large enough n. Meaning, if you unravel this, so what does it mean when we unravel this? It just means for all epsilon greater than 0. Let me just maybe first unravel this part. This means that xn lies in this interval ultimately, which is saying, if we do not want to use this phrase, this says that for all epsilon greater than 0, there exists some n such that whenever little n is at least capital N, we have xn is in this interval. So that's what this statement really means, right? So after a certain point, all the points of the sequence lie in this interval. Now this point will depend on the value of epsilon. Once you choose an epsilon, this n comes into existence, but this n may be very, very large. That's okay. That's not a problem. Okay, so this is what is the definition of convergence is. And we will look at examples, but let's first establish some notation that we will frequently use. So if xn converges to x, we write many things. We write either this, or we may write this. So these are one of the two ways to express it, but a lazy notation is the following, or two lazy notations are. So the lazy version is this or this. This is kind of the full version where you are treating n as the dummy index, while here it is somewhat improper, but in context this is fine. And similarly here you are expressing that as n goes larger and larger, xn comes closer and closer to x. That's kind of the motivation or the spirit of this notation, but of course it is referring to this whole gory statement. Or you may just write that, and in context this does not cause any confusion. So these are some notations. Also, if xn converges to x, so this is more of a definition. So if a sequence xn converges to x, we say x is the limit of xn. So that's just a phraseology. The point to which a sequence converges is called the limit of the sequence. Now one may object, why are we using the definite article here? The use of the definite article is sanctioned once we can prove that there is a unique such x. A priori, it may be so that a convergent sequence has multiple limits, right? We have defined a sequence, so we haven't even defined what is a convergent sequence. We have only defined convergence to a point x. So before even so this is fine. So if a sequence converges to x, we say x is the limit of xn, but it is unclear if a sequence possibly can converge to two different points. It cannot. That is a simple fact. We will look at it. But as of now, let's just believe for the moment that if a sequence converges to x, then it cannot converge to anything else. It will only converge to x. So the use of the definite article is sanctioned. And now we can define a convergent sequence. So let xn be a sequence. A real sequence, of course. We say xn is convergent if there is a real number x such that xn converges to x. So in the notation that we have discussed, we may just write this. So that's a convergent sequence. A sequence is convergent if it converges to something. Okay. Hopefully I'm not missing anything. So one more thing. If a sequence is not convergent, then it is called divergent. So that is also a definition. A sequence that does not converge is said to diverge or is called a divergent sequence. So it is becoming all hodgepodge. Let me make some space. Is said to diverge or is called a divergent sequence. Okay, a lot of terminology, but they are all very interconnected, so I'm sure they don't cause any confusion. All right, and for example, maybe I should take a separate page for examples. So here are two examples that we want to discuss. They are very, very basic. Okay, so this is our sequence. We saw this sequence in picture previously. So if you plot it as natural numbers on the x-axis, you will see something like this, a kind of a, something that kind of clearly goes to 0. So what we want to say is that this thing is convergent. In fact, what we really want to say is this is 0. Right? So why is this? Well, first of all, we know that infimum of, so I'm just explaining this a little bit. So we know that infimum of this thing and a natural number, this is 0. This is what we use to prove the Archimedean property. So using this fact, we can show that this is the case. How do we show this? So to show this, we need to first fix an epsilon. So fix an epsilon greater than 0. And we want to show that xn lies in this interval ultimately. Right? Which is to say, let me recode it. Which is to say this is the case. Right? But now using this fact, we know that there are things here which come this close to 0. So I'm waving my hand a little bit, not being very, very formal, but we know by star, where star refers to this equation, that there is an there is a natural number n such that this thing happens. Because if there were no natural number for which this happens, then the infimum wouldn't be 0. It would be greater than 0. Right? So this happens, but once this happens for one n, it happens for all the larger n's. And therefore, this thing happens whenever little n exceeds or is at least capital N, which is to say that 1 upon n is less than epsilon ultimately over n, which is to say xn in absolute value is less than epsilon ultimately over n. And that's it. So that's almost a complete proof of this statement, and you can fill in the details that you find missing. Okay, what about this guy? That guy does not converge. So we want to say that then xn does not converge. Right? So why is this? Well, the thing is that if you visualize this sequence, this is 0, this is 1, and this is -1. So whenever n is even, xn is here, and whenever n is odd, xn is here. So it is oscillating ping pong for even, odd, even, odd, even, odd. Okay. Now if this were convergent, if this converged to something, let's say x is here, let's say x is neither 1 nor -1, then around this neighborhood, and we can draw a neighborhood around x which does not contain 1 or -1, then we get a contradiction because xn does not lie ultimately in this neighborhood, right? Because it is either 1 or -1, but neither 1 nor -1 would be in this neighborhood. All right, so the only candidate for the limit of this sequence is either this or that. But the same problem arises. If this were the limit of the sequence, you draw a small neighborhood around it which does not contain -1. It would mean that ultimately all the points of the sequence are here, but that is not the case because for odd values of n, the sequence takes this value, which is not here. So you will see that there is no real number to which this converges, and hence this is not a convergent sequence. It's a divergent sequence. Okay. So much for this, and yeah, let's continue. So let's now establish the uniqueness of limit. It will be very, very simple. Suppose we have a sequence of real numbers and we have two things, x and y, to which xn converges. Then we want to show that x is equal to y. Why is this? So assume x is not equal to y, and we will bring a contradiction. So let epsilon be half or maybe 1/3 of the distance between x and y. Okay? You'll see why we have chosen such a thing. In pictures, this is x, this is y, and this is the distance between x and y. You choose epsilon so small and now make intervals of width 2 epsilon around x and y. So what would they look like? They would be disjoint. Something like that. Right? So maybe I'll label this is y plus epsilon. And similarly for the x's. So this point is x plus epsilon, this is x minus epsilon, this is y plus epsilon, this is y minus epsilon. And these two intervals will be disjoint simply because of the choice of epsilon. Right? This much is only 1/3 of this total distance. This much is only 1/3 of this total distance. And hence there cannot be any overlap between the two. In the picture I have x greater than y, but you can, it's not really sensitive to the picture. The argument that we are giving is not sensitive to the picture. So now by this fact, by the fact that xn converges to x, or rather xn converges to x, we know that xn lies in this interval, or maybe I will write it this way. This happens ultimately. But in fact, it's better to write it the previous way. So xn lies here ultimately, meaning xn lies here ultimately, and yn lies here. Sorry, xn lies here ultimately. But what is going on? These are two disjoint subsets, both in which xn lies ultimately over n. And now if you use the star marked problem, you will see that there is a contradiction. So thus we have a contradiction by the star marked problem. That's it. So this establishes the uniqueness of the limit of a convergent sequence. Okay. Finally, we have this notion of tending to infinity or minus infinity. So start with this real sequence xn. We say xn tends to infinity if for all natural numbers we have xn greater than n ultimately. Right? That is the definition of tending to infinity. We also sometimes may say converging to infinity, but I want to avoid that phrase. So what's going on is you have this real line, somewhere there is 0, and we have this sequence xn. It says the following: you choose whatever big number you want. After sufficiently long time, all the points of the sequence are exceeding that thing. So they kind of go towards infinity. So this definition is capturing the phrase very nicely. Okay, so that's the definition of tending to infinity. Similarly, you can define for yourself tends to minus infinity. A very analogous definition can be given. And maybe let's just take one example very quickly, very basic example. Just define xn equals x for all n. So then, sorry, not x, xn equals n for all n. So if you define this, then it is clear that this tends to infinity, and notationally we write, the notation for this is this. So when we have xn tending to infinity, we may write this. So then here I just want to say that here indeed this happens. You can easily prove this. And for another example, define this thing. Xn is the square of n. Here also same thing happens. Okay. So very, very basic things, and note that very simple observation. If xn tends to infinity or minus infinity, if xn is plus or minus infinity, then xn does not converge, meaning xn is divergent. Right? Because if it converged to a point x, after a certain point it would be trapped inside an interval around x, but that cannot go hand in hand with this condition, because you choose capital N much greater than this, away from this interval. Then you have xn lying here ultimately and xn lying here ultimately, but both cannot happen simultaneously. Again, the star mark problem can be used. So this automatically implies divergence. So we have this picture. We have a real sequence. They are of two types. One is convergent, the other is divergent. Meaning if you do not converge, then you diverge by definition. And divergent sequences can be broken into two categories: those which either tend to infinity or minus infinity. They are much like convergent sequences, but here kind of convergence is happening outside the real numbers, so we do not call it convergence. And then there are these other ones which diverge, but they do not tend to infinity or minus infinity. So it's a small picture that one can easily remember. Alright, so much for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.